Welcome to this video on Year 2 Pure Chapter 8 Prep Practice on Parametric Equations. So question 1, we want to find the x and y axis intersects of a curve given parametrically by x equals t plus 5 and y equals t squared minus 4. Remember that whether we're doing the parametric equations or not, if you want to work out where a curve intersects the y-axis, you want to know when x is 0. So if we do that with the equation x equals t plus 5 and say that we want x equal to 0, that means that t plus 5 is 0, means that t is minus 5. So putting t is minus 5 into the x equation gives us x is 0. Putting t is minus 5 into the y equation gives us y is 21. And so this parametric curve crosses the y-axis at 0, 21. Likewise, if we want to know where the curve crosses the x-axis, we put y equal to 0, which gives us t is 2 or minus 2 from the y equation. Putting each of the values of t is 2 and t is minus 2 into the x, we get that actually it crosses the x-axis at two places, 7, 0 and 3, 0. Okay, so it's very much the same kind of things we've done with Cartesian equations, except that we're doing our work via the parametric value of t. Question 2. Find the Cartesian equation of the curve with parametric equations x equals 3 over t, y equals t plus 2t squared. In trying to find the Cartesian equation, what we want to do is find a single equation that relates x and y. In other words, we don't want t. So this gives us a clue that what we want to do is to eliminate t from these two equations. So think of them as kind of solving these simultaneous equations, but where we're going to get a relationship between x and y. That's going to be our solution, if you like. And we're going to do it most easily by eliminating t, by getting t as the subject from one of these equations. And the easiest is going to be, in this case, for x, because if x equals 3 over t, that means that t equals 3 over x. And if we substitute that into the y equation, we can get y in terms of x. So when we have this kind of situation, just think of eliminating the t. Question 3. We want to do the same kind of thing, get the Cartesian equation, but this time there is a trig expression that involves t in both the x and the y. And trying to get t as a subject would be difficult here. Need lots of possible values for t when we have sine of t, and likewise for cos of 2t. So trying to get t as being inverse sine of x minus 3 over 2 would be problematic. So the easiest way of working with Cartesian equations when the parametric equations involve trig is to find a trig identity that relates the trig expression, in this case sine of t, and the trig expression, in this case cos of 2t. And that identity is that cos of 2t is 1 minus 2 sine squared t. And then what we do is we obtain the sine of t in terms of x. So sine of t in terms of x is x minus 3 over 2, rearranging this equation. And rearranging this equation, we get cos of 2t equals y minus 1 over 3. And if we then substitute those into the identity, we get that cos of 2t is replaced by y minus 1 over 3. The sine of t is replaced by x minus 3 over 2. And because we need sine squared, we need to square that. And that will now give us a relationship between x and y. A parametric equation is being converted into our Cartesian equation. Now, we want also part B to find the domain and range of f of x, where y equals f of x. So in this context, this means that we want to find the allowable values of x and the allowable values of y. So the domain of f of x can be the values that x can take, and the range is going to be the values of f of x, or in other words, y can take. Now, if you look at the Cartesian equation, you would imagine that x could take any value and y could take a value up to and including 4. But because we've got parametric equations that lead us to this Cartesian equation, actually they're more limiting. And if we look at the parametric equation for x, x equals 3 plus 2 sine t. We know that sine of t has a maximum value of 1 and a minimum value of -1. So sine of t varies between -1 and 1. So 2 sine of t will vary between -2 and 2. So when we add 3, the whole thing will vary between 1 and 5. Okay, so that is the domain that we've been required because it's the interval of values that x can take. And likewise, if we look at y, the cos of 2t varies between -1 and 1. So 3 cos 2t varies between -3 and 3. And if we add 1 to that, the y will vary between -2 and 4. So if you were to draw this Cartesian equation for these parametric equations, you would need to limit yourself to this box, if you like, of values, and we wouldn't get the remaining Cartesian equation graph that you would think from the equation that we get for part A. So quite an important note there. Question 4. Find the values of parameter t at the points of intersection of the circle with the Cartesian equation x squared plus y squared equals 1 and the line with parametric equations x equals t plus 1, y equals t plus 2. When you want to find the intersection of curves, you want to solve the equation simultaneously. And that's going to be the case whether both equations are Cartesian, or in this case, one of them is Cartesian and the other one's parametric. And in this case, we want to solve them simultaneously. And the easiest thing going to be to substitute the value of x by t plus 1 and the value of y by t plus 2 in the Cartesian equation. So in the Cartesian equation, x squared plus y squared equals 1. If we replace x by t plus 1, replace y by t plus 2, we're going to get a Cartesian equation. Okay, and then if we want to, we're going to get a Cartesian equation replaced by an equation involving just t's. If we then solve this equation, which is a quadratic, we get our two values of t, which in this case are -1 and -2. If we then want to get the Cartesian coordinates of where they meet, we just put t's -1 into the x equation here and the y equation here, and that will give us the x and y coordinates when t is -1, and when t is -2, we get the other one. So these are the Cartesian coordinates of where these curves meet. Question 5. This is an example, although it's pure maths, chapter 8, that it overlaps with mechanics projectiles, because what we have here is the x coordinate is the horizontal position, the y coordinate is the vertical position. But anyway, treating it as a pure maths question, find the initial coordinates of the stone. Well, we just put t equal to 0, and t equals 0 gives us x is 0, and t is 0 gives us y is 2, and so the initial position is 0, 2. Find the coordinates when the stone is at the maximum height. Well, the height's given by y, so if we differentiate, put equal to 0, we get t is 1, and then put t is 1 into the original equations, we get the coordinates are 5, 7. And if we want to get the Cartesian equation, we're going to eliminate t from these two equations, and the easiest way of doing that is to get t is x over 5 and substitute that into the y equation to get y in terms of x. Okay, I hope that was useful.